Here's a brief explanation of Newton's three laws of motion. Newton's first law, also known as the law of inertia, is a fundamental principle in physics that describes the behavior of objects in motion and at rest. An object at rest stays at rest, meaning it will not move unless a force acts upon it. Similarly, an object in motion stays in motion at a constant velocity unless acted upon by a net external force. This could be anything from friction, gravity, or even a push or pull. This law means that if nothing is influencing an object, it will not change its state of motion. For instance, a feather floating indoors will eventually come to rest due to air resistance. For example, a ball on a flat surface will stay still unless someone kicks it, applying an external force that changes its state from rest to motion. And a rolling ball will keep moving in a straight line unless friction or another force slows it down. Friction is a force that opposes motion, causing the ball to eventually come to a stop. Similarly, a book resting on a table remains at rest until an external force, like a push, acts on it. This push provides the necessary force to overcome the book's inertia. A moving car will continue to move in a straight line unless acted upon by an external force such as friction or a collision. Friction from the road and air resistance gradually slow the car down, while a collision can abruptly change its motion. In the vacuum of space, where there is no air resistance, an astronaut or satellite will continue to move indefinitely unless acted upon by another force. This illustrates the concept of inertia in a frictionless environment. Understanding Newton's first law helps us comprehend the natural tendency of objects to resist changes in their state of motion, whether they are at rest or moving. This principle is foundational in the study of physics and essential for explaining everyday phenomena. Newton's second law, also known as the law of acceleration, is a fundamental principle in physics that describes the relationship between force, mass, and acceleration. According to this law, the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. This means that the greater the force applied to an object, the greater its acceleration will be. Conversely, the more massive an object is, the less it will accelerate in response to the same force. This relationship is often written as the formula F equals ma, where F represents the net force applied to the object, m stands for the mass of the object, and a denotes the acceleration produced. This simple yet powerful equation helps us understand and predict the motion of objects under various forces. Newton's second law explains how the velocity of an object changes when it is subjected to an external force. For instance, when a skateboarder is pushed, they gain speed, illustrating how force affects acceleration. For example, if you push a shopping cart, it will accelerate more if it's empty, which means it has less mass, than if it's full, which means it has more mass. This demonstrates the inverse relationship between mass and acceleration. Additionally, more force results in more acceleration. This is why a sprinter exerts a lot of effort at the start of a race to achieve maximum acceleration, and why a cyclist pedals harder to increase their speed. Understanding Newton's second law allows us to comprehend the dynamics of motion in our everyday lives. Newton's third law, often stated as, "For every action, there is an equal and opposite reaction," is a fundamental principle in physics. This law means that forces always come in pairs, known as action and reaction forces. When one object exerts a force on a second object, the second object exerts a force of equal strength in the opposite direction back on the first object. This can be observed in everyday situations. For example, when a ball bounces off a wall exerts an equal and opposite force on the ball. For instance, when you jump off a small boat, you push down on the boat, action, and the boat pushes you up into the air, reaction. This is why the boat moves in the opposite direction. Understanding Newton's third law helps us comprehend the interactions between objects and the forces they exert on each other in various scenarios. Let's summarize Newton's laws and delve deeper into their significance. First law. Objects maintain their state of motion unless acted upon. This means that if an object is at rest, it will stay at rest, and if it is in motion, it will continue moving at a constant velocity unless a force acts on it. For example, a stationary car will not move unless someone pushes it, and a rolling ball will eventually come to a stop due to friction. This principle is also why astronauts in space, where there is minimal friction, can float and continue moving in the same direction until they encounter another force. Second law force equals mass times acceleration. How much an object accelerates depends on its mass and the force applied. This law explains why heavier objects require more force to move the same distance as lighter objects. For instance, an athlete pushing off starting blocks exerts a force that propels them forward. A car accelerates faster when more force is applied to the gas pedal, and a rocket launch demonstrates the immense force needed to overcome Earth's gravity. In weightlifting, the amount of force an athlete needs to lift a weight is directly related to the mass of the weight and how quickly they want to lift it. Third law forces are reciprocal. Every action has an equal and opposite reaction. This means that whenever one object exerts a force on another, the second object exerts an equal and opposite force on the first. For example, when rowing a boat, the oars push against the water and the water pushes back, propelling the boat forward. Similarly, when a person jumps off a boat moves in the opposite direction. Two skaters pushing off each other will move in opposite directions, and pressing down on a spring causes it to push back with equal force. This law is also evident in the recoil of a gun when it is fired. Newton's work in the 17th century revolutionized our understanding of the physical world. His laws of motion laid the groundwork for classical mechanics, a branch of physics that describes the motion of bodies under the influence of a system of forces. Newton's insights were pivotal during the scientific revolution, influencing not only physics, but also astronomy, engineering, and beyond. His work with early telescopes and his formulation of the law of universal gravitation were monumental in advancing our comprehension of the cosmos. These laws are fundamental to understanding how objects move and interact in our physical world. They apply to everything from the motion of planets in space to the mechanics of everyday objects. Traffic moving on a busy road follows these principles, as do children playing with a ball, engineers designing and working on machinery, and the celestial dance of planets orbiting the sun. Newton's laws provide a framework that helps us predict and explain the behavior of objects in motion, making them essential to the study of physics and engineering. In everyday life, these laws are applied in numerous fields. In sports, athletes rely on these principles to optimize their performance, whether it's a sprinter accelerating off the blocks or a basketball player calculating the perfect shot. Engineers use Newton's laws to design everything from bridges to vehicles, ensuring they can withstand various forces. Astronomers apply these laws to predict planetary movements and spacecraft trajectories, enabling space exploration. Newton's contributions continue to impact modern science and technology profoundly, demonstrating the timeless relevance of his discoveries.